Good afternoon and welcome to this webinar titled Simulating Magnetic Clutches in SOLIDWORKS. My name is Arvind Krishnan and on behalf of EMworks, I welcome you all for today's webinar. We will be shortly starting. Okay, good afternoon and let's briefly look at the agenda that we have for today. I'm going to start with telling you a little bit about EMworks, the company and its products. Then we will get to the topic for today, which is simulating magnetic clutch in EMS for SolidWorks. And so we'll get on with some basics of the magnetic clutch. Then we will do a live demonstration for you where I will be showing you a simulation of a magnetic clutch in SolidWorks by using EMS for SolidWorks. Then we will talk about EMS products and bundles, and then what is it that I need in terms of the products to be able to do a similar simulation. And finally, we will have some time for Q&A. I just want to remind you, this particular session has been recorded and a recording of this video will be sent to each one of the registries. Okay. So if you have any questions, just one bookkeeping item before I proceed to the next slide. You should see a chat window in the GoToMeeting and you are welcome to type in your questions in the chat. And towards the end of this meeting, I will be going over some of the questions that you have for this webinar. Okay. With this, let me get started with some basics about EMworks as a company and the products that it offers. EMworks products are gold partner products to SolidWorks, which means that it is really the #1 choice for electromagnetic simulation for SolidWorks users. There are two particular products that is there in this category. One is the low frequency electromagnetic simulation that is called EMS for SolidWorks, and the second one is the high frequency electromagnetic simulation, which is called HFWorks. For low frequency electromagnetic simulation, which will be the product that we will be looking at today, well, we can do a wide variety of applications. We will look into that towards the end of this presentation, and also during the demonstration you can have an idea of what are the different capabilities within the software. And the high frequency electromagnetic simulation, which could be a topic for a different day, is basically a product that is embedded inside SolidWorks, which can be used by RF and microwave engineers to study and simulate passive RF and microwave components. Okay? Now, over 500 customers worldwide use EMS as their preferred solution to do their EMS electromagnetic simulations. And one of the main reasons that you will see very shortly is that it's when you're a SolidWorks user, it's extremely easy to use and you have a very short learning curve compared to some of the other programs out there in the market. Okay, let us start with the magnetic clutch. Now, what is a magnetic clutch? So magnetic clutch is actually an electromagnetic device that is used to transmit torque from one shaft to another. Now, as you see here, I have a cross section of a magnetic clutch design. There can be several design variations of the magnetic clutch, but mainly most of the magnetic clutches will be able to perform a similar type of function as alluded in this particular design. There is this rotating part which is brown in color, as you see here, rotating part, stainless steel. It is labeled. That's I would say is a driver component where the driver shaft is fixed to that particular part and it rotates. Okay. Then we also have a rotating part which rotates only when it is in contact with the driver. That's a little bit brownish, grayish in color in the back. It's a ferromagnetic substance, as you see here, rotating part, ferromagnet, and that is the follower. Okay, so when the driver and the follower are engaged, that is when the clutch is engaged, then there is a torque transfer that happens between the driver and the follower. There are also two other main components that are very critical to the functioning of a magnetic clutch. That is the coil, and the coil is made up of several conductors of copper. It can be wound. Several conductors of AWG copper wire is wound, and then that comprise a coil. And there is also a ferromagnetic core. Okay. So really, the 3D model is shown in the right here, and we will actually be looking at this model inside SolidWorks. So what really happens when the coil is energized? So when you pass a DC current through this coil, there is going to be a magnetic flux that is going to be induced because of this current, and this magnetic flux is going to circulate in the ferromagnetic core that surrounds the coil, and this flux goes through the air gap and is linked with the driver, which is non-rotating at the beginning, as a result, there is going to be a force acting on the driver, which makes the driver go towards the the follower go towards the driver. So let me repeat it. So when the clutch is activated by passing a DC current through the coil, there's going to be a magnetic flux in the ferromagnetic core. This magnetic flux creates a force on the follower that helps it to go get engaged with the driver. As a result, the torque transfer happens. We're going to see it a little bit in some kind of an animation here. So as you see here now, there is no engagement between the follower and the driver. So you see here the driver is rotating, but the follower does not rotate. And if you see here closely, there is a small gap, an air gap between the driver and the follower. And this air gap is not closed because there is no current induced. There's no current through the coil. Now what happens when the clutch is engaged? Now you can see here that both the driver and the follower rotates, and this is because there is no gap here. So there is a complete engagement between the driver and the follower, and due to friction there is no slippage, and hence torque is transmitted. So you can see that as the driver rotates, the follower rotates as well. This is really the basic principle of an electromagnetic clutch. Now let us look at the simulation. Let me quickly jump to SolidWorks and take you through how a simulation is performed in SolidWorks using this magnetic clutch. Now before we do that, let us establish some of the objectives of the simulation. Okay. The first objective of the simulation is to determine the force of attraction of the plate when the coil is activated. So just as the coil is activated, what is the force with which the driver is being attracted towards, the follower is being attracted towards the driver. Okay. The next objective is going to be when the clutch is fully engaged, that means the driver and the follower are in contact with each other. At that time, when there is still an excitation of the coil, what is that force with which these two, the bonding force, basically they bond together. Then we also will try to look at how to visualize the magnetic flux densities in the model and understand if any saturation happens in the steel components. Okay. So with this, let me go back to SolidWorks, and now as you see here in SolidWorks, this is the model of magnetic clutch assembly. Let me take a section view, and this helps you to understand the magnetic clutch as you saw during the animation and also in the previous slides. So just to recap, there is the driver, which I've highlighted now. Then there is the follower, there's a coil, and there is a ferromagnetic core around the coil. Initially, there is no contact between the driver and the follower. As a result, there is no torque transfer that happens. So when you spin the driver, only it spins. The follower does not spin. Okay. Now next is what happens. Now the first objective is when I apply a current, what is the force with which the follower is going to get attracted towards the driver? That's the first objective. Let us see how we can accomplish that in EMS for SolidWorks. So the first step that you do in EMS is to create what is known as a study. So let me go ahead and as you see here, EMS is a gold certified add-in product for SolidWorks. So you can, the look and feel of EMS is very similar to what you have experienced with your SolidWorks CAD, and it's right embedded right inside your CAD. So you design your components in SolidWorks and you can do your electromagnetic simulations right here. So the first step is to create a study. Here I'm going to create a study. There are several different study types that are available for you in EMS. The study types are magnetostatic, which is what we will be using for today's magnetic clutch simulation. There is also AC and transient magnetic, and these are the magnetic simulations that are possible inside EMS. We also have electric simulations. We have electrostatic, electric conduction, and AC electric. Now, EMS has the ability to do multiphysics. You can couple the simulation to thermal, structural, and motion. Okay? And these topics will be taken up in future webinars. So the first step is to create a study. Here we create a magnetostatic study, and then we say OK. Once we create a study, now we need to apply materials. Now, before we apply material, there is something that I do want to highlight here, the concept of air. As you know here that the magnetic flux travels both in the ferromagnetic substance and also through air. It propagates through air. So it is important to model air, and that is done very simply by creating air as a component inside SolidWorks, as you see here. Okay. So let us apply material. So we apply air to the air component. Now EMS comes with its own material database. It comes with a wide variety of commonly used materials, and it is a fully customizable material database which allows you to create your own materials and use them for simulation. Here let me apply air material to the air component. And now that we have done that, I can go ahead and hide this component so that we can work with all the main parts of the magnetic clutch. The coil is made of copper, so I'm going to go ahead and apply material. From the conductors, I'm going to apply copper. The core and the follower, they are both made of ferromagnetic substance, in this case steel 1010. So let me go ahead, apply materials, and I open the nonlinear folder and go to steel 1010. And here you have all the associated material properties like the BH curve, conductivity, etc. that are required for electromagnetic simulation. They're already predefined for you by the program. And this is the driver, and the driver is made of a non-ferromagnetic substance, in this case stainless steel. So once you apply materials, the next step is to define our coil. So for that, let me go ahead and activate the section view. It's very easy to now look at inside the coil and understand its features when you activate the section view. So I can create a coil. I'm going to create a coil. And I select the coil component from the screen. I also select the face perpendicular through which the current goes in. As you see here, this is the current carrying conductors are here, and this is the direction of the current. So here I am going to make it as 18 gauge, and there are 340 turns, and a current of 2 amperes is applied. Notice that with 340 turns and 18 gauge, this area, you can get almost 88% filled with copper. And I guess that's pretty much the best that can be done here. The program also tells you that, gives you that feedback. So once you make a coil, you select OK, and then you have defined a coil. And the last thing that we need to do before we run a simulation and look at the result is going to be looking at the force. So we would request EMS to compute the force acting on my follower. So I select the follower component, and this tells the program to compute the force acting on the follower. Let me go ahead and hide the coil direction so that it's much cleaner. Now, just for the sake of time, I have already pre-solved this particular problem before this webinar. So let us jump straight into looking at the results. Okay, so it's really the same problem I've set up as a separate study which has been solved earlier. So the first result that I would like to look at is the force acting on the follower. So that can be read directly from the results table dialog box. You can see here that the force is in the minus x direction of the global coordinate system of SOLIDWORKS, and the force is about 14 newtons. Okay. Now this is the initial force with which the follower will get attracted towards the driver because of the excitation of the coil. Now one can also look at several other result plots. Like here I have a section plot of the magnetic flux density. Now this tells me how the magnetic flux propagates through a section here. Okay. I also have vector plots. Now the same magnetic flux tells you in the form of vectors, you are able to see how strongly the flux lines are coupled and what is the magnetic circuit that goes from the ferromagnetic core into the follower. Okay. And you can also look at it in the front view. You see here that there is a gap between the driver and the follower because this is not a condition where they are engaged. Now as you excite the coil, there is going to be flux associated with the follower, and as a result there is going to be a force of attraction that moves the follower closer towards this electromagnet, and that force is 14 newtons. Now let us go back to our next objective, and that objective is what really happens when we engage the clutch, when these two come into contact with each other. So I have created another configuration that helps me to look at this scenario visually in SOLIDWORKS. Now this is a case where there is no gap between the driver and the follower, so it is completely engaged. And now we would like to know what is the force acting on the follower. Now to be able to do that, one needs to do another simulation just like what we did earlier. And EMS helps you to clone studies, which is very useful because you don't have to duplicate things that were already done. So by simply you can drag and drop study 1 and create another study, in this case say study 4, and use the configuration which is clutch engaged, and then immediately EMworks creates a new study where all the materials are predefined. The coil is already defined as before, and also the request for the force has been defined. So this is a very important productivity feature that helps you to duplicate studies without the effort that was done earlier. So as before, I have a new study, I have a previous study that was run, so we can jump right into the results. So let us now look at the result table to find out the force. Now you can see that the force of attraction, the bonding force between the driver and the follower, is close to 27 newtons. Now contrast that with 14 newtons that we had earlier, so it is almost 2 times the force. So this is the bonding force. And one can also take a look at the several plots that we took a look at for the previous one. Here I would like to bring it back to the view. You can see that these two are in contact with each other, and you can see the magnetic flux lines, the magnetic flux density as a section plot in the model. You can also look at it here, in a more of a 3D environment, a magnetic flux density plot, and as well as the vector plot. So here is the magnetic flux density as a vector. Now, in addition to the magnetic flux density, one can even look at the magnetic field intensity. Now, basically, you can see what happens in the air gap and so on. So it's very easy to compare results between studies too. So I can go ahead and compare the value of say just study 1 and 2, basically the value of the force, and you can take a look at the force values as a proper plot. You can see here that at study 1, where there is a gap between the driver and the follower, we had about 14 newtons, and when they are in contact we had about 27 newtons. So EMS makes it very easy to do these design comparisons and model changes that help you to understand your simulations and your designs much better. So with this, let me revert back to my PowerPoint. Now let's again recap on the objectives for the simulation. We determine the force of attraction when just before there is engagement, and that was about 14 newtons. And then when the clutch plate is fully engaged, we had about 27 newtons. We visualized the flux density. We also understood what are the areas inside the core which had very high values of flux density, and you were able to visually compare using quantitative values that you saw in the color chart to see if there was any saturation. Okay, and we noticed that design change where we had the clutch, the driver and the follower engaged with each other. That was a design change, and how you can simply by drag and drop deal with any kind of design changes in SolidWorks. Okay. So with this, let us go back to the product bundles. As I said earlier, EMworks comes with two standard flagship products, EMS for SolidWorks and HFWorks. HFWorks is the high frequency product for RF and microwave designs. EMS is the product that we looked at today. And EMS has two main bundles. One is EMS Professional, another is EMS Premium. Now, EMS Professional comes with 6 different study types: electrostatic, electric conduction, AC electric, magnetostatic, which was the topic that we saw today, AC magnetic and transient magnetic. And one can do multiphysics simulation where you can couple to thermal stress, motion, and structural. Now let us quickly look at a product-wise application of EMS. As you see here, the low frequency, one can do electromechanical component design and simulation. We can have motors, generators, linear actuators, magnetic recording devices, clutches, magnetic brakes, etc. Solenoids, they can all be analyzed using EMS. One can also do, design sensors. You can do wireless power charging, power transfer devices, power electronics devices, high voltage application, transformers, bus bars, etc. And also in the high frequency, mainly we are dealing with antennas. We are also dealing with RF and microwave passive components like couplers, waveguides, etc. So what we did today, which is the simulation of a magnetic clutch, what you would require is a version of SolidWorks which is 2015 or above. Currently SolidWorks is at version 2018. And EMS Professional, which is also at version 2018. So what you would need, if I just go back to this, is everything that you saw today can be done with our base EMS Professional package. Now, again, thank you very much for attending today's webinar on behalf of EMworks. I appreciate your time, and I thank you all for attending today's webinar. As I mentioned earlier, this webinar has been recorded, and a link to this webinar will be sent to you in a couple of days. Should you have any questions, you can visit our website, emworks.com. You can get valuable information like white papers, customer testimonials, or you can visit our YouTube channel for over 60 videos covering various aspects of our product. You can also see our past webinars from our YouTube channel. For contact regarding sales, you can call us at this toll-free number, or you can email us at sales@emworks.com. And don't forget to download a free 15-day trial version of EMS by visiting our website. So you can participate in downloading our trial version, and you can check for yourself the power of EMS and how it can solve your own designs. With this, we conclude this webinar. And thank you, and see you again on a future webinar.